Name is Curtis Brown, and I am joined once again by Steve Kukoska and Tom Dick. We are talking about being off on a tangent, which I land off on a tangent pretty often, especially during these calculus sessions. I end up having to do all kinds of approximations to the questions that Steve asks me. And so I think I've worked in almost all of the title into that introduction. Steve has got some great problems that he has written for us to kind of check out tonight, and Tom has certainly done his work getting ready for the technical aspects and being able to show us some great things on the TI-84. Without further ado, I think I'll turn it over to you, Steve.
All right. Thank you very much, Curtis. Gee, I hope you're prepared tonight, Curtis. We have lots of questions for you.
I'll tell you what, I have not done my homework tonight.
Oh,
I'll
no.
wing
Oh,
it.
no.
And I'll count on the folks in the chat to bail me out, Mark and Wanda and Steven and several of the other guys that bail me out on a regular basis.
All right. Well, we'll see about
Maybe
that.
there'll be a few students in the chat
Oh,
that bail
good.
me
That would
out
be good. That would be
tonight when I haven't done my homework either.
All
I'd
right.
sure.
Well, we've got lots of problems tonight that deal with tangent line approximations, of course, and we've got one towards the end, if we make it towards the end, that is a particle motion problem. And we've got some higher order derivative questions in here that in my mind specifically appeal to good problem solving skills and pattern recognition. So we're going to start out by looking at some tangent line approximations. These are, in my opinion, Curtis, very typical sort of AP calculus exam questions, but asking about tangent line approximations from maybe a little bit different perspective. So from different views, different ways to answer some of these questions. So let's take a look at this first one, which we'll think of as calculator active. So this is, we've got a function f of x defined to be x squared e to the minus x. And the very first thing we want to do here is find the equation of the tangent line to the graph of f at x equal 2.5. Again, very typical of an AP exam question. Well, just to add a little bit here, in order to do this one, I'm sorry, I'm a little off to the side here, Curtis, still trying to write on my tablet, my remarkable here. We do need to find the slope and we need a point. We need a point on that tangent line and we need the slope. And so the very first thing I tried to do here was to find this point. I know that x is equal to 2.5. So I plugged that into the expression for f. Here is the decimal answer. I want to remark and remind people that I am writing that to 3 digits to the right of the decimal, and I tend to round. But I'm also storing these values in my calculator to a greater degree of accuracy. I need to find the first derivative, and I need to use that in order to find the slope. So in order to find the first derivative of this expression, I need to use the product rule. Now, of course, if I have technology in front of me, I don't need to do this analytically, and Tom may show you some of this. But I'm going to start out by doing this analytically anyway. First function times the derivative of the second plus the derivative of the first times the second. And I did a little bit of simplification here. I think I was able to factor out an x and an e to the minus x out of both of those terms. And I need to evaluate that expression at 2.5 to find the slope. And here's my numerical answer to 3 decimal places, rounded. And I guess if I really wanted to, and some students do this on the exam, is they might leave this as in sort of an analytical form. Let's see if I've got this right. This is a minus 0.5, I think, inside that parentheses. So this would be a minus, I think, 1.25 times e to the minus 2.5. And again, some students would keep that as the analytical expression, the exact expression for the slope. So an equation of the tangent line, point slope form here, y minus y1 is equal to the slope times x minus x1. I did a little simplification over here. There's the equation of the tangent line reported with 3 digits to the right of the decimal. Again, I've stored that slope to a greater degree of accuracy, and I have stored this 0.770 to a greater degree of accuracy, which is the 0.513 value times, let's see, brought to the other side. So I have a minus 0.103 times a minus 2.5, and then I brought the 0.513 to the other side. So it's stored to a greater degree of accuracy on my machine. So, all right, I want to use that tangent line to approximate the value of f at x equal 3. So bluntly, all I need to do is to come up here to this expression and plug in a 3. One comment I'll make here, Curtis, is that I have used the appropriate symbol here, approximately. I'm really finding an approximate value for f of 3. In the past, we have not docked students, or we have still, the better way to say this, is we have still allowed students to earn this point even if they put an equal sign in there. That's not correct, but we still allow them to earn this point. I did a little simplification there. I got a 0.462. Good. Let's go on to some more interesting questions about this problem. It says, let's see, is this estimate in part B an overestimate or an underestimate? Well, let me see if I can arrow up first a little bit here. There we go. And justify your answer. Well, how do we do that? Curtis, how do we do that in general?
Sorry, I just got a phone call and I had to hand my phone over to my wife. What? No, I mean
So,
that is absolutely what happened.
yeah, and the dog ate your homework too. The estimate in part B an overestimate or an underestimate. So I've used this tangent line approximation.
Oh, the estimate in part B, where you
Now,
have
how do I
is equal
determine
to
that? What's the
0.0.
general idea here? How do I
So,
determine if that's an overestimate or an underestimate? What do I have to
well,
do here?
just making sense of what the picture is that I see down at the bottom down there that but because it's concave down,
Good.
I'm going to expect that your approximation is going to be an overestimate.
Yeah, and in
'Cause-
general, what we need to do is we need to check concavity here.
yeah.
And one common error here, or misconception, is that we only have to check concavity at one specific value, and that's not true. We really need to check the concavity of this graph of f in a neighborhood that contains this 2.5 and 3. We want to know about the concavity of the graph of f in a neighborhood that contains those 2 points. So here's what I did to solve this. I first started by finding the second derivative, and forgive me, I'm going to try to write a little bit here up at the top or off to the side here, just to remind myself. I had the first derivative of f, and let's see, I found that to be equal to x e to the minus x times x plus 2. So how do you find the derivative of that expression? Well, this is a good problem, at least in my mind, because, well, we need to use the generalized product rule. So how do we do that? We take the derivative of each one of these individual expressions, multiply by the other two, and add the whole thing up. So here's the derivative of the first times the product of the other two, derivative of the second, product of the other two, derivative of the third times the product of the other two. All right, now I know you did this, Curtis. I did a little simplification and I arrived at this expression. And I just want to think about that for a minute. I'm trying to determine concavity of this graph of f. There's the expression for f double prime. So I need to determine, at least a way to do this is to determine the sign of f double prime. And at least when I looked at this initially, it's not so clear. Here's what I saw. I know that this expression, this exponential expression, is always positive. So I'm left with figuring out what the devil does that quadratic do. And so what I tried to think about is, well, first of all, is it always positive or is it always negative? And the answer to that is no. And so I had to solve that quadratic for x, and I arrived at these two values of x. So I'm going to scribble a little bit off to the side. This is not drawn very well to scale, but I'm going to draw a sign chart. So let's see, I've got 2 minus the square root of 2 2 plus the square root of 2. I'm going to call this row x, this row f double prime of x. And I know that f double prime of x is 0 at those two places. And I'm going to think a little bit more about this. Let's see, where's 2.5 and where's 3 in these intervals? Well, 2.5 and 3 are actually in the middle there. They're between those two values, right? Because the square root of 2 is what, about 1.4 or so?
1.414.
So let's see. I know that 2.5 and 3 are in this interval in here. So I'm really going to be interested in the sign in that interval. Well, let's see. Thinking a little bit about this, and we all have different ways of doing this, but the sign over here in this interval of f double prime is positive. It's negative over here, and it's positive over here. This is a pretty standard sign chart when we're dealing with a quadratic that has two roots, two real roots like that. All right, so what does this tell me? For x in this interval, f double prime is positive, pardon me, f double prime is negative, and that means in this interval, the graph of f is concave down. So we found a neighborhood that contains those values in which the graph of f is concave down, and that tells me that I found an overestimate in part B. I really like that problem. There's lots of little things going on in there. Too excited about this, Curtis. You always kid me about that. But I've got the generalized product rule going on there. I've got a sign chart that I haven't interpreted, not just a sign chart alone, but I've interpreted that sign chart. And I finally arrived at this conclusion that I have found an overestimate. I'm going to finish off this problem with one more part down at the bottom, if I can arrow up a little bit. This is just one of my pet peeves. Curtis, Tom knows about this. You know, we don't use the calculator to do a lot of confirmation these days. You know, I found an answer. Well, let's look at the technology to sort of confirm that my result is correct. And so with this graph at the bottom, I've actually graphed y equal f of x. I've got a point on there, 2.5.513. Remember, that was the point at which I wanted the tangent line. If you can see the color in here, the graph of f is in blue. The graph of the tangent line is in green. There's the point on the tangent line that was my estimate for f, 0.462. And you can just about see the concavity in there, and you can see that that estimate is indeed an overestimate of the actual value of f. That's pretty cool. Now, Tom may have the opportunity to do this. He may have the chance to graph this on the calculator, and that would allow you to zoom in a little bit more and maybe see this overestimate a little bit more clearly. But for me, that's pretty good. That's nice. That's at least a first try here at confirming this result. Cool. Tom, a little technology?
Sounds good, Steve.
Okay, here we go. All yours.
Okay. Fire up my TI-84 here. And looks like you've got it up. You can let me know. Is that showing up all right?
Looks good, Tom.
Okay. So yeah, I just wanted to go through a few calculator basics on this nice problem involving the tangent line. So what I'll start out with is going to my y equals menu and putting in the function that was under discussion here, which was x squared times e to the negative x.
Good.
And so we'll get that negative x in there. Enter that. Looks good. And we could go ahead and just do a quick graph of it. I'll do a zoom decimal window here. There's the graph. I think Steve's graph just showed probably to the right of 0.
Yep.
But this is a graph. Scaling's a little bit different here than what Steve had, but it looks pretty reasonable. And now just going through the calculations we needed for that tangent line. let me quit from the graph and just go to the calculator screen. And let's see, we needed a point and a slope. So first of all, let me get the point was, let's see, 2.5.
Correct.
Well, we're going to need the y value that goes with that. So let me bring up the y1, where we have our function, and evaluate that at 2.5. And I'm going to go ahead and store that in, I'll just use A. So that's the y value that goes with 2.5. So that's the point of tangency that we're interested in. And now we need the slope. So let me pull up the math menu, scroll down there to nderiv, that's for derivative. Oh, we get this nice derivative template. We're going to take the derivative with respect to x, again of y1. So let me pull up y1. And we want to evaluate that at 2.5. And let me go ahead and see what kind of number we get. Okay, looks like what Steve got. But I want to also just go ahead and store that answer I just got. So when I hit the store key, since I didn't have something in front of it, it looks at whatever my last answer was and says, okay, I'll put that, store that in whatever you want. And let's be real imaginative and store that in M for slope. How's that? Okay.
Okay.
So there's our slope is stored away. And now if we go back to our y equals menu, let's see, I want to build the tangent line equation. So we want that slope times the quantity x minus 2.5. And then let's see, well, when x is 2.5, we should get that value a. Well, looking at this, if x is 2.5, that first term will be 0. So I just need to put my a here. This would be similar to, you just did the algebra with paper and pencil.
Yep.
It's our tangent line. And now let's graph both together. Ah, there we go. One thing I did want to look at and make a comment on, Steve, here is your question about overestimate and underestimate. You actually gave a very specific value, x equal 3. Let's say, okay, let's use the tangent line to approximate there. I'm going to trace, and let me go to the tangent line, and I could arrow over to 3. Or I could just type in 3 and jump there. Okay, so that's my tangent line approximation.
Right.
But if I just up or down arrow, I'm going to see what the actual function value is. And I can see that that's a little bit less. And if I forgot what it was, I can just go back and forth. There's 0.461 something. That's the tangent line approximation. And this is the actual value. So we could just say, just by comparing those two values, that the tangent line approximation is an overestimate. However, so that wasn't using any kind of second derivative concavity analysis there.
Yeah.
So the question might arise, well, did Steve kind of go over the deep end doing all this concavity stuff? But let's say the question had been, if you use the tangent line approximation to approximate the function value at some number c between 2.5 and 3, would it be an overestimate or underestimate? In other words, I didn't even give you the value. I just told you what interval it was in. Now you've got to use an analysis like what Steve did, because I mean, I can't just compare the two values and say, oh, this one's bigger than that one, or vice versa. I'd have to somehow argue. I don't know, it's in there somewhere, but given the interval where he had to analyze the concavity, he had it good. Now, this is something I think a lot of people have tried this before, and I think initially it's surprising, though it shouldn't be. I'm going to go back to 2.5. And if I compare values there, well, they're exactly the same. Well, that's by design. That is the tangent line equation right there.
Right.
But what would happen is if we zoomed in on this point, okay, how would the graphs look? So let's go ahead and do a zoom. I'll do a zoom in. And now that, let's see, let me go ahead and hit the trace again. There we go. And I'll hit zoom again, zoom in again. And you can see that those two graphs are looking more and more alike.
Mm-hmm.
In fact, I keep hitting the trace here, and then we'll do a zoom in again. I'm doing that trace thing so I actually get right on the point of tangency each time. So let me do a zoom in again. And let me do it one more time. And here we can hardly distinguish between the two graphs at all. And that's to be expected. That is what it means when we say that tangent line approximation is the best local linear approximation at that point, meaning it's the unique line that can't be distinguished from the function graph if you zoom in enough. So it's this idea of best linear approximation is really fitting on this local level. When we talk about like data points, like a scatter plot, we're doing a regression line. Well, that's a best linear approximation of a different sort. There's a different way that's being judged. This is best linear approximation at this particular point. And that's what is meant by the tangent line approximation. And, oh, I'll do one other thing. Let me just do
So,
yes, go ahead. Questions?
we just had a little bit of a discussion in the chat here about the likelihood of a question like this on the exam. And it seems like this is one you might expect in either the free response or the multiple choice sections of the exam. Is that fair to say?
Yeah, and these concavity arguments, like what Steve did, those are often ones you have to do, but it likely wouldn't be at a given point, but it would be at some point you wouldn't know. You would have to use concavity.
Yeah, the point of the question would be more about using concavity and that sort of second derivative analysis type stuff, right?
Right.
Okay.
So I think the last thing I'll do before turning it over to Steve is sometimes get a question of, well, we've got the numerical derivative to evaluate the first derivative. Is there a way of evaluating the second derivative at a point? And well, let's give it a shot. What I'm going to do is I'll just bring up my math menu and bring up derivative. And let's see, derivative with respect to x, but now I'm going to take the derivative of the derivative. Okay, so I'll bring up the math menu again. And so you can see I've got the derivative nested within the derivative operator that I had before. So we'll do y1. And here's where you want to be a little bit careful. If I was to put my value 2.5 here, let's say I wanted, well, what's the second derivative equal to at x equal 2.5? If I put 2.5 here, then what's inside the parentheses will evaluate to just be a number. And when I take the derivative of just a constant number, I'm going to get 0. So here inside, we're just going to put an x here. So that's telling it to think of that as a derivative function. And then we'll put the 2.5 out here. And there's the value of the second derivative at x equal 2.5. Notice that it's negative, so that's indicative of that, well, concave down behavior.
Concavity, yeah, concave down sort of behavior. One question that kind of popped up, or suggestion or idea, is there any benefit to looking at the table to help you with some of this analysis here? Does that shortcut some of this? You can kind of see a few of these things happening or not? I don't know.
The table is certainly a good feature to look at. It's not, I might be just being a little bit dense here. I'm not seeing a real, other than maybe looking at evaluating the function at a specific point, but then I
Sure.
find the calculator screen is as
Just
easy
as
as
helpful.
anything.
Yeah, just as helpful.
You have to
Yeah,
think
I
about.
agree with that. I agree.
I can maybe see it for seeing about a series of values if you needed to evaluate.
Exactly. If you're looking at a sequence of values, now I love to use a table there or use the lists in some way or other. Yeah.
Right. Right.
All right. I think I will stop my share and turn it back over to Steve.
All righty. Very good. All right, Curtis, here's problem number 2, and I have to confess, I really like this one. There's some cool stuff going on in this problem, I think. So here in this problem, we have 3 functions, f, g, and h, and they look very different to me. We have f, which is actually a quadratic. We have g, which is an exponential function. And we have h, which is, well, it's a log plus a constant. So very different looking functions. And what we want to do is find an equation of the tangent line to the graph of f, the graph of g, and h, all at x equals 0. And I wonder if there's anything interesting going on here, and how the devil do we explain this result? So let's see here what's happening. So, all right, I have to do the same sort of thing here. I've got to find a point. I've got to find the slope. So here we go. I'm going to attack this one analytically. Eventually, maybe look at a graph. So I have to find f of 0 first. I'm going to plug that in. If I've done that correctly, the point here is 0, 1. So f of 0 is 1. So this goes through the point 0, 1. I have to find the equation of the tangent line to the graph of f at the point 0, 1. I need to find the first derivative. Well, there are actually a couple of ways that I could do this. I could, if I really wanted to, multiply that out first, but we'll use the chain rule. This is 2 times x minus 1 to the first power times the derivative of the inner function, which is just plain 1. So I'll evaluate that expression at 0. I've got 2 times a minus 1, so there's the slope. So, all right, I've got the slope with the tangent line. I've got a point that it goes through. So this equation is just y equal minus 2x plus 1. Is that right? Yeah, minus 2 times x minus 0. So plus 1. So that's pretty easy. That's pretty straightforward. So I'm just thinking a little bit about this and what the graph might look like. I know x minus 1 squared is a parabola. I'm thinking about this tangent line. I don't think it's not horizontal, but okay, I think I understand what's going on in the background here. Let's take a look at G. Well, I've got to find the point on the graph of G where x is equal to 0. So I plugged in an x equals 0. There's a minus sign in there, but this is still e to the 0. So that returns a 1. So son of a gun, I've got the exact same point here. The graph of G also goes through the point 0, 1. What's G prime? Well, again, chain rule here. It's e to the minus 2x times the derivative of that exponential function, or what's in that exponent, which is just minus 2. Evaluate that at 0. Let's see, e to the minus 2 times 0, e to the 0 is 1. That's, oh no, wait a minute, what's happening here? The slope is also minus 2. So this tangent line has slope minus 2, goes through the point 0, 1. The equation of the tangent line is exactly the same. Wait a minute, f and g are really different. but they have the exact same tangent lines at 0, 1. Wait a minute, this can't be happening. Let's take a look at h of 0. I'm going to plug in an x equals 0 in the function h. Well, let's see, that's 2 times a 0, that's a 0, so I'm going to be taking a log of 1, which is 0. There's a 1 out in front. Oh no, this also goes through the point 0, 1. What's the derivative of h? Well, let's see. The derivative of 1 is 0. How do you take the derivative of a log here? I've got the log of an expression, like the log of u. That's the derivative of that expression divided by the expression. So let's see. The derivative of that argument is -2 divided by the argument. I don't see any simplification there. So I'll evaluate that at 0. That drops out. Oh no, the slope there is also -2. The equation of this tangent line is also -2x plus 1. Curtis is thinking, how long did it take him to search for these functions so that this would happen? So here's what we've got. We've got 3 very different looking functions. All go through the point 0, 1. All have the exact same tangent line at the point 0, 1. How do you explain this? Well, just so happens that each one of these functions that has 0, 1, that go through 0, 1, whose graphs go through 0, 1, also have the same derivative there, -2. Does that mean they're the same graph? No. But what's happening right there at 0, 1 is, well, there's some common things happening there. So let's see if I can get a graph of this. I don't know if Tom can do this better with technology. I produced this with Mathematica. There are some colors in there. Let's see. I think my tangent line is in black. F is in blue, G is in green, and H is in maroon. So they're all really close together around 0, 1. And okay, I believe this graph. This is sort of confirmation for me. I see that tangent line. It's tangent to each one of those graphs at the point 0, 1. Notice the scale on the x-axis here. So for which function is the tangent line the best linear approximation close to x equals 0? Well, the answer here, and Tom alluded to this just a little while ago, is that all of them. The tangent line is the best linear approximation that we can find for each of these graphs. But what happens as we move farther away from x equals 0? Well, let's see. As we move farther away from x equals 0, it kind of looks like, and I'm going to use this word in quotes, I guess, close. It kind of looks like the graph of f is closest or remains closest to that black tangent line. So that as we move farther away from x equals 0, it kind of looks like the tangent line approximates f just a little better than h or g. That's a neat problem, the way that works.
Hey,
like
Steve,
yes.
There's an interesting question happening here. I don't know.
Uh-oh. Go ahead.
I already gave my answer to it. So
Okay.
I'm going to wait for you to respond. So somebody asked if this could be that you might say that those curves are tangent to each other at that point. And I supposed that, yes, you could say that, but only because it's not a point of inflection. We're not changing concavity at any one of those points. So we don't have a point of one of those curves isn't going through the others. Instead, they all do just touch at that point.
One point. I don't know. Tom will have to help me here, but I don't know if I can recall or have seen a definition for 2 curves being tangent to each other.
I have.
Okay, shoot, Tom.
And I'm going to need to correct you a bit, Kurt.
Oh, fantastic, Tom. I love it when I'm wrong.
I mean, I understand what you were saying. The thing is, a graph like x cubed, the tangent line at x equals 0 cuts through the curve. And so, but we would still say the tangent line is tangent to the cubic graph at that point. But to the question at hand, though, we say that two curves are tangent to each other at a point if they have the same tangent line at that point.
Really?
So all of these curves, including the tangent line, are tangent to each other.
And so the
even if we
concavity doesn't,
intersect, yeah. Okay.
So the
And it kind of
concavity
fits
doesn't
with circles. We can talk about circles being tangent to each
Sure.
other
Yeah.
if they share a tangent line. And that's where it's circles that the idea that a tangent line can't cut through a curve sometimes comes up. But once we move away from circles, because the concavity can change, it can end up intersecting.
So,
and especially like you said, at an inflection point, you could have.
so
And-
Curtis,
So even if one of these had had well, if we had a curve that was tangent along all of these others, but it was also the point of inflection,
And it also crossed
through one of these, we could still say that it was tangent.
Still say they're tangent to each other. Yeah.
Wow. Okay.
But it's interesting. It's all boils down, if they share a tangent line, they're tangent to each other.
Fabulous. See, look at that. That is
Pretty
fantastic.
cool.
Similar to the common tangent in geometry. I love it.
Pretty cool.
Good stuff.
Tom, should I continue or do you have something else here?
Well, I could do a real quick share if you don't mind.
Okay, sure, please.
And I'll make it very quick.
There you go.
Let me share my 84 again. And I tell you, just to save time here, I went ahead and entered all these functions.
Okay.
So the y equals menu, I've got your three functions. And I've got your tangent line too. So it's basically all four of the graphs. So let me just go ahead and do a zoom decimal. See them. And let's see, the point of interest was what, 0, 1, right?
Yep.
I'm going to go ahead and move my little crosshair up there to 0, 1. There we go. And now I'm going to do a zoom in. And since I'm centered right at that point, I can just hit enter over and over again.
And what's going to happen here?
Oh, look at that.
Yeah.
People do it. Wow. Look at that. The graphs just look like they're all on top of each other. I'll do one more. There they go. Boom, boom. See the color. They graph so fast that you have to see the color change. But at this zoom in, they all look identical to each other. Now, they're not quite. If I was to turn on the trace and move a little bit off of 0 and then switch between my functions, you would see a very, very slight difference. Oh, boy, there's not much of a difference at that value, is there? Let me move a little bit.
Not at that one, no, Tom.
Oh, okay. Now I'm seeing a little bit of difference in that last decimal place.
Yeah, yep.
But notice my first pixel over, and I couldn't even distinguish there. So great. Okay, that's all I had, was just a chance to zoom in on that cool set of graphs.
Okay.
And let me stop the share and turn it back to you.
Very good. Okay, we can probably zip through this number 3. We've got some other interesting problems here, but I wanted to do this one because it does, of course, involve a tangent line approximation, but I think it's a little bit different, and this is the type of thing we might see on the AP exam. So in this particular problem, we have a function f. We don't have an equation for it or an expression for it. However, we do know that f of 2 is equal to -5, and we have the graph of the derivative. And although it's written down here, I'll write it a little bit bigger just for emphasis here. This is a graph of the derivative, the first derivative of f. And so what I want to do is find an equation of the line tangent to the graph of f at x equal 2. Well, I've already got the point. That was given to me up here when x is 2, y is equal to -5. And how do I find the slope this time? Boy, this is classic AP exam type material. How do I do this one? Well, I've got to go to the graph of f prime, and I've got to read the slope from the graph here. And on Curtis, I'm not sure that this is visible, but there are grid lines in here. And of course, there would be, I believe, on a problem like this on the exam. So let's see, at x equal 2, I think it's going through y equal 4. And so the slope here is 4. What's the equation of the tangent line? Well, y is equal to 4 times x minus 2, x minus x1, plus y1, so -5, and a little bit of simplification. There's an equation of the tangent line. Okay, so real quickly here, let's suppose I want to use that tangent line to approximate or to estimate, excuse me, f of 1.9 and f of 2.1. Well, I plug those values into that expression for the tangent line over here. Here are my two approximations. And are they overestimates or are they underestimates? Let me arrow up just a little bit here if I can. And this is how I answered that one. I don't have an expression for f here, so I've got to use some idea related to concavity here. So I notice from the graph of f prime that it is decreasing in a neighborhood around 2, including 1.9 and 2.1. So my conclusion is, since f prime is decreasing in that neighborhood, that f is concave down, and therefore my two estimates are overestimates. So I can't graph f here. I don't have an expression for it. But this is a really cool problem to use concavity to answer this, given the graph of f prime. I really like that. Good. All right, here's another one. Suppose there's no known formula for g, but we know that g of 1 is 5. Here's another similar type problem. Use the tangent line to the graph of g to approximate at x equal 1 to approximate 1.05. Well, again, I know the point right off the bat is 1.5. We're given that here. There's no known formula for g. Remember, well, we do know g prime. We don't have the graph this time, but we have g prime. Geez, Curtis, I wonder if I really wanted to. Wonder if I could integrate that. We'll leave that as a challenge question. We'll get back to that. So
that seemed like a hint.
You think so? I don't know. So wait a minute. What's g prime of 1? Well, g prime of 1 turns out to be 0. This is interesting. So the slope is 0. So this is a real easy tangent line. It's a horizontal line, y equal 5. And so an approximation for g at 1.05 is just 5. Well, is this an overestimate or an underestimate? Well, in order to answer that one, I'm going to have to take a look at g double prime. And the way that I did this is I first attacked this analytically. I found the derivative of g double prime analytically by using the product rule. And then I graphed g double prime. And I said, well, you know what? I can see that g double prime is positive in a neighborhood near 1 that includes 1.05. So that means the graph of g is concave up in that neighborhood, and that means I have an underestimate. So that's another different way here to get at these tangent line approximations and ask, are they underestimates or are they overestimates? So if I were writing questions for the exam, I'd write some like that. They're a little bit different, but test your knowledge in a good way. And here's something that Tom may be able to do on the 84. I'm not sure, but I did this with the Nspire because this is in keeping with one of my themes for tonight, which is confirm. You know, we do a lot of exploration and then we solve problems analytically, and then we use the technology to confirm our results. And so here's what I did. I can actually use the fundamental theorem of calculus here to write an expression for g of x because I know that g of 1 is equal to 5. And so I've got an expression right here for g of x. So I can actually plug that into my calculator, that circled expression. And the technology will actually evaluate that and give me a graph of g of x. I might not be able to come up with a closed form expression, but darn it, I can find that graph of g. And so I did that. I graphed the tangent line, which is y equal 5, a horizontal line. And you can see from this that indeed that is an underestimate, because I can see that as I move over to 1.05, I am above that tangent line. I have a value of just a little bit bigger than 5 in the what? 1, 2, 3, 4th decimal place? That's really cool, I think. That's a really nice visualization to confirm my result and making use of the fundamental theorem of calculus, which is terrific. Tom, should I keep going?
Well, I could show that on the 84 if you'd like, Steve.
Okay, how about that?
Okay.
Okay.
All right, so pulling up my TI-84 here, and just wanted to look at that fundamental theorem of calculus idea. Sometimes people are not aware that you really can graph these definite integral functions like Steve defined there.
Yeah.
So I'm going to go to my y equals menu, and first of all, I'll just put in the original function that Steve had, which was I think e to the negative x squared.
Yep.
And that was times natural log of x. Interesting function.
Yes, sir. I might have typed in that in. One thing we often fail to mention here, Tom, and it's my fault, is, we should remind students and teachers that when we see functions like this, and there's no mention of the domain, the functions are defined on all real values of x for which you can get an answer here, for which the function is defined.
Right.
So clearly this is not defined for all reals. Okay.
Right. It's just going to be defined for x greater than 0.
Right.
Okay. So basically, if you have if this is your derivative function and you have an initial condition for the original function, this case, I think it was g of 1 equals 5.
Yes, that's correct.
Well, we'll put in the 5. And then we'll create a definite integral with 1 as a lower limit and x as an upper limit. That's way when x is 1, that integral will be 0, and we'll get our 5. So let me pull up the math menu, go down there to number 9, an int, lower limit of 1, upper limit of x. Now I don't have to type this again because I've got it in y1. Just go to pick up our y1. And if you want to be make this look, I think, a little nicer, I'll put the of x. You don't really need to do that on the calculator, but I think it's better form. And there's
Is there any harm, Tom, in using a t in there?
Probably not. And some people would say, yeah, it would be better form to use a variable of integration that's different than this.
Yes. Okay.
Let's go ahead and give this a shot, see what the graph looks like. And I'll just do my usual zoom decimal. We got the graph of the original function pretty quickly.
Indeed.
I don't know if you can see up in the upper right-hand corner, looks like my calculator's busy. Is it? Let's see, is it working away?
So you perhaps did not see that because I believe, what's your Y max, Tom?
Okay. So it may be.
So you got to go up to at least 5 to see this.
Good point. So the graph may be off the screen.
I think it is, Tom.
Okay. All right, so let me change my window here. And I'm going to also change my X min to 0.
Yeah, good.
Because we're not going to see anything to the left of 0 anyway. And let me go change my Y max to, I'm just kind of taking a guess here. Let me try 20.
Okay.
And we should at least see something, I think, there. Ah, here we go.
Here it is.
And good catch, Steve. And wow, this is kind of interesting. Your function at e to the minus x squared, that factor goes to 0 so fast.
Yeah.
That means the slope of my original function is going to be going to 0 real fast. So it's getting very horizontal very quickly. So these are making sense. Here, my derivative graph, it looks like it's, let's see, this is the original graph.
So that's the derivative. That's right. That's negative, and the function is decreasing.
So what is it? Is it still less than, a little bit less than 0 after to the right of x equal 1?
Well, e to the minus x squared is positive.
Right.
And log of x would be positive once we pass 1.
Aha. So it really does cross at x equal 1. It does become a little positive. And we don't have to leave this to guessing. We could do a trace. Let me jump over to 1. Okay, there, my derivative is equal to 0 there. I'm just going to go a little bit to the right of 1. Yes, it is positive. Okay. So that slope. So that's my original function, which is the derivative of this function here, which means there's actually a minimum.
Right.
At x equal 1. Isn't that cool?
It is cool.
Imperceptible here. It looks like it's just flattened out, but there really is the tiniest little dip there. So that's what calculus does for us. It gives us the analytic tools that something that would escape our eyes, we can actually get to analytically. All right, let me stop the share there unless you want to look at something else here.
Oh, that's great. Great. Thanks, Tom.
Back to you.
Okay. Okay, deal. Here we go. Sorry about that. Extra click. All right. I'm not going to go through this one in gory detail, but this is a nice one, teachers, for tomorrow morning at 8 o'clock. Here's a function f, which involves some trigonometric expressions, functions, chain rule. I want to find the fourth derivative of this function. So just working through analytically, knowing the chain rule, knowing the derivative of trig functions. And I just wanted to point out something at the bottom here. Tom knows that I enjoy using the TI-Nspire, and one of the coolest things to me is that this will give you answers, where possible, that are exact symbolic answers. And so you can actually find the fourth derivative on the TI-Nspire exactly symbolically, and there it is. That's really cool.
Provided you have the TI-Nspire.
Provided you have the cast version. Yes. Thanks, Tom. Right. This one's interesting too for 8 o'clock tomorrow morning. G of x is equal to x e to the x, and somebody had the gall to ask, can you find the 40th derivative of this function? Well, all right, I'm going to start off by taking a couple and see if I can find a pattern. I really like this problem because it does sort of emphasize this idea of pattern recognition, which I believe, as you know, is very important to problem solving. If I take the first derivative here of this expression, I've got to use the product rule. First times the derivative of the second, derivative of the first times the second, and a little bit of simplification. That looks interesting. X plus 1 e to the x. G double prime first, derivative of the second plus the derivative of the first, which is just 1, and a little bit of factoring and simplification. Oh, I'm beginning to see something here. The third derivative works out to be x plus 3 times e to the x, and son of a gun, I'm going to draw a conclusion here. Then the 40th derivative is x plus 40 times e to the x. That's pretty cool. And I hope you can see my calculator screen there. I've used the TI-Nspire once again, the CAS version, to find the exact symbolic 40th derivative of that function, which is just unbelievable, isn't it? The technology can do that. That's really cool. All right, let's at least start this one if we can. Let's try a particle motion problem. This is technology active, so maybe Tom can end up doing a little bit with technology here. A particle moves along a line here, a horizontal line, so that its position at time t greater than 0 is given by that expression. Holy Toledo. It's got a trig function, it's got an inverse trig function, and it's got a log function. T is measured in seconds, s in feet. Find the velocity of the particle at any time t. Well, I've got to do this symbolically. So to find the velocity, I've got to take the derivative of that position function. Derivative of sine is the cosine. Derivative of the arctangent, just as sort of an aside, I think I've seen this question pop up in the Facebook page a couple of times. The students have to memorize that particular derivative, and yeah, they should know that one, I think. Minus the derivative of the log of t plus 1, well, that's the derivative of the argument divided by the argument, and I don't see much simplification there. Okay, Curtis could, if he really wanted to, get a common denominator in those last two expressions and combine them, but I don't think that's necessary. Find the velocity of the particle at time t equal 4 seconds and indicate the units of measure here. Wow, that's typical AP exam lingo. V of 4, if I plug that in, I had to go to my calculator to find this answer. I think it's 0.795. And again, Tom and Curtis know that I generally round rather than truncate. I think the units of measure here would be feet per second. And I have a calculator screenshot down at the bottom. I've started it out by defining my function s. And this was very interesting. I had actually forgotten about this. I haven't done one of these in a while. I took the derivative of s and evaluated at t equal 4. And son of a gun, the calculator gave me the exact symbolic answer, which is really interesting. So as an aside on the exam, if you had a problem like this on the calculator active portion of the exam, it is understood that students may be using a CAS machine, and we would certainly accept that exact symbolic answer. There would not be a need to convert that to a numerical approximation. You could, but you can keep it as the symbolic answer. How do you see that as a symbol, pardon me, as a numerical answer on the CAS machine? Well, there are a couple of ways. You can actually hit the approximation key to do this, but I like to do this by somehow putting in my expression one of the values in the expression with a decimal point. So evaluate this first derivative at t equal 4 with the decimal. There's the minus 0.795. Pretty cool. All right, for t between 0 and 10, when is the particle moving in the positive direction? Well, what's the conceptual idea here? I have to find those places where the derivative of the position or the velocity is greater than 0. Well, a way that I'm going to attack this is I'm going to graph that velocity, and I'm going to find those places where the velocity is bigger than 0. So there's actually a lot of things going on in my screen illustration here, in my calculator screen illustration. First of all, notice that I didn't have to actually enter in my analytical derivative of the position function. I can just have the calculator graph the derivative of s. Once it did that, I went into the menu here, and I actually found the zeros of that function. So I now know where the velocity is 0, and I can see on this screen where the velocity is greater than 0. So to answer this question, looking at the screen, looking at my zeros that I found, the velocity is 0, is positive over here. It's positive over there. Those are the intervals on which the particle is moving in the positive direction. That's a neat problem. A little bit different way of solving that one.
It's a nice
And let's see. Go ahead, Curtis. I'm sorry.
I said that was a nice one.
I like that. And to finish up here, find the acceleration of the particle when t is equal to 4 seconds and indicate the units of measure. Well, all right, I went and found the second derivative analytically and plugged in an a equal 4. And I did that on my calculator and noticed that I can also find the second derivative of that analytically. What is that? 89 divided by 7,225 minus the sine of 4, which is too cool. And the second derivative, the numerical approximation, is 0.769. The units here, I believe, would be feet per second squared. Well, that's pretty good, Curtis. I think if you give me one more second, I think I had a challenge question here for people to look at. Maybe that's down the bottom here. Ah, yes, here it is. I had one more part to this. Is the particle speeding up or slowing down at t equal 4 seconds? We'll leave that. But the challenge question here is, for t between 0 and 10, when is the particle speeding up and when is it slowing down? So this is a little different. I'm not asking about what's going on at one particular value of t, but I want the intervals on which the particle is speeding up and the intervals on which it is slowing down.
Ooh, that's a nice.
I like that one.
Yeah, I like
Okay.
that. That's a great way to wrap up
Beautiful.
that problem.
Excellent.
Very creative. What, Steve? I am always amazed. Probably shouldn't be, but I'm always amazed at your creativity. This is a nice problem set tonight. So thanks for
Thanks,
sharing
Curtis.
that.
I think so too. Some good problems for tomorrow morning.
Yeah, good problems for 8 o'clock tomorrow morning when I'm wide awake, ready to go. Probably not so great for 8 p.m. On a Monday night. Hey, just a reminder, teachers, I've seen a few of you guys already emailed me. Oh, somebody said we could go based on absolute min and max. That's an interesting strategy there. Yeah.
Oh, it is. It is. I didn't think about that. That's very good. That's not
Yeah.
the way I was going to attack this, but that's very good.
Yeah, I like that. I like that for the challenge question. So, yeah, really nice idea. So, really quickly, teachers, some of you guys have already done this. If you're interested in getting some professional development hours, you can certainly send me a link or a email. I put my email there on the chat. It was great to see you guys. Great to see all of you out there joining us, being active in the chat. Thanks for answering each other's questions and for engaging Tom and Steve as well. So I will go ahead and make sure that we get the solutions posted tomorrow.
Yes, sir.
We'll also post the questions for the next go round.
Yep.
Which will be November the 18th, I believe is the Monday night there. So we'll see you guys back here in 2 weeks.
Very good. Thank you, Curtis.
Take care, everyone.
Bye, everybody.
All right. We should be, boy, that was quick. We ended